Hello and welcome back. Today we're going to look at some more notes. This is our third set of notes so far, and the topic for today is the rational root theorem. So we're continuing with our journey on solving polynomial equations, and the rational root theorem is kind of a big deal. This is one of the highlights of our polynomial unit. Now, what we're going to learn today is, it's not a whole lot of new stuff because really we've practiced solving these equations. We know how to do it, but what the rational root theorem is going to do is it's just going to help us get a start on solving these. So let's take a look and see what it says here. Let's see. In order to factor and solve, we needed to know either a factor or a zero. Remember, zero means a solution. So here's the question that the rational root theorem is going to help us with. How can we find possible solutions if that information isn't given to us? Because what you'll recall is that all of the equations we've solved so far, we've had a little help to get started. It told us maybe something like this: x equals 2 is a solution. And then we say, okay, we know this solution, so now we can do synthetic division and continue the solving process. Or maybe they gave us a couple choices. Maybe it looked like this. And they said one of the two is a solution. And then we said, okay, well, we can try this one, see if it equals 0. If this one doesn't work, let's try this one. Then this one will equal 0. But what the rational root theorem is going to help us with is if that's not given at all, if all we have is equation, polynomial equation, and it says to solve, well, how do we even know which numbers to try to check and see if they're solutions? The rational root theorem is going to give us the list of numbers that are possible solutions. So that's the only thing that we're adding here, just this little extra bit at the beginning of the process. And then once we find the solution, it's what we already know how to do. The solving process from there is exactly the same. So let's see here. Some stuff that we need to know first here. We're going to talk about some types of numbers. The first one is an integer. You know what this means? What kind of a number is an integer number? Well, here it is. It's a whole number. And it can be any whole number as long as it's a whole number. It doesn't matter if it's positive or if it's negative or even if it's 0. Okay? And yes, 0 is considered a whole number. So some examples, 5 is an integer, 12 is an integer, negative 37 is an integer, 15.6 is not an integer because 15.6 is not a whole number, it's a decimal. So if there's a decimal, not an integer, but if it's a whole number, it's considered an integer. Okay, the next type of numbers here, rational numbers. What is a rational number? Tells us here, a rational number is any number that can be represented as a fraction like this. So number on the top, number on the bottom. Here we're using P and Q to represent the numerator and the denominator. So any fraction of integers, so meaning as long as I have an integer on the top and an integer on the bottom, then what we have when we consider that entire fraction, it's called a rational number, a ratio of fractions. Remember, a ratio is another word for a fraction. And of course, we have this to look out for right here. Q cannot equal 0. That's because Q is the number that we're dividing by, and we can't divide by 0. If you try to divide by 0, we don't get an answer. It's undefined. So that's the only one that we can't have. But other than that, any integer can be in the top or the bottom of the fraction. And here, let's take a quick look at some examples. So look, 1/2, that's 1/2. That is a rational number. 5/3, This is a rational number. Okay, so here's a list of examples. Rational numbers, some are positive, some are negative. What would also be considered a rational number is a decimal value because this fraction has an equivalent decimal. So if it's a decimal like this, 0.5, that's also a rational number. This one right here, 5 over 3, that's going to give us 1.6, where the 6 is just repeating 6 forever. That's also a rational number. So we can have a decimal value is considered a rational number as long as either the decimal value ends. So here with 0.5, it just stops at the 5. Or if that decimal value just repeats. So 1.6 and the 6 is going forever. That's a repeated decimal. That's also a rational number. But an example of a decimal that's not irrational, like let's say one of our famous ones, pi, which is 3.14159. That's all that I have memorized of it, but then it keeps going forever. So this decimal keeps going forever, and it never repeats. This decimal here, the 1.6, this also keeps going forever, but it's just the same number. It repeats. So because it repeats forever, it's a rational number. But with something like pi, when you have an infinite decimal that never repeats, that's not rational. It's actually what we call irrational. So this one, not a rational number. But other than that, a decimal will be a rational number. Hey, what's the decimal value here for 8 over 2? 8 divided by 2 actually simplifies to 4, a whole number, an integer. So take a look here. 4, which is an integer, is also a rational number. So what we're seeing here is that any integer is also considered a rational number. Okay, so that's that. Integers, rational numbers. And let's see here. All right, let's see what the rational root theorem tells us. Okay, the rational root theorem. A polynomial function with integer coefficients. Let's see, where did it go? Okay, here we are. A polynomial function with integer coefficients will have rational solutions of the form p over q, where the p values can be any factors of the constant, the q values can be any factors of the leading coefficient. Okay, so what does this mean? All right, a polynomial function with integer coefficients. And you know what? That's all that we're dealing with here is integer coefficients. Like if you look at these problems, all of our integers, they're all whole numbers. These are the only equations that we're dealing with. So everything that we're dealing with, integer coefficients, the rational root theorem is going to apply. And then what it says here is, okay, so if it has any rational solutions, so any solutions that are fractions or whole numbers, they're going to be in this form, p over q, where p is factors of the constant. Now the constant is the very last coefficient. So look at whatever the factors of that are. Those could be in the top of the fraction. The bottom of the fraction, our q values, are factors of the leading coefficient. So that's the coefficient in the very front. Okay, so we'll see an example right now, see what this actually looks like. Okay, so what does this tell us here? This provides a list of possible solutions. Yeah, so this list that we're going to get from P over Q is only possible solutions. We then will have to check and see, does it actually work? Does it satisfy the equation and actually make it equal to 0? Okay, and this is an important one here. Don't forget to include both positive and negative. So when we do a P over Q, we get a number there the possible solution could either be the positive version or the negative version of that number. Okay, so let's take a look here. Let's do this first one together. Now, the directions here. Use the rational root theorem to find all possible solutions to the following polynomials. Okay, so we're not actually going to solve and do the whole process. We're just going to figure out what are the possible solutions. So number one, here's our polynomial. And let's say that we have this equal to 0. So now we're ready to solve it. So let's figure out what our P over Q options could be. Well, let's start by figuring out what are the P numbers. P numbers are factors of the constant. What's the constant here for this equation? It's a 2. So the P values are going to be all the factors of 2. The factors of 2 are only 1 and 2. So that's what we have for our choices for P. Okay, and then Q is factors of the leading coefficient. All right, so let's look at the leading coefficient. Remember, the leading coefficient is the coefficient in front of the x with the biggest exponent. And as long as your equation is in standard form, that's always going to be the front number. So 6 is our leading coefficient. All the choices for Q are going to be all of the factors of 6. So you could look up the factors of 6 if you if you wanted to make sure you don't miss any. But what do we have? 1 times 6 or 2 times 3. Those are the choices. I'll list those out in order here. So just counting up, we got 1, 2, 3, 6. Okay. All right, there they are. So let's go ahead and make a list of all of our possible solutions. So the possible solutions are going to be every combination of a P number divided by a Q number. So every combination we get here with one of these on the top and one of these on the bottom. So let's start to list them out. And this is what I'll do. I'll start by using a Q value of 1, and I'll see what combinations that we have. So we could have 1 divided by 1. 1 over 1 simplifies, of course, to just a 1. So 1 is a possible solution. Now let's not forget to put plus or minus because it can be positive 1 or it could be negative 1. Okay, staying with the Q value of 1, but moving to the new P value, look, here's a combination that we could get 2 over 1. 2 over 1 is, of course, a 2, so 2 could be positive, could be negative. So what we're doing here is we're generating a list of possible solutions to this equation. All right, let me move to Q value of 2. So we could have 1 over 2, so 1/2. And then here's another combination here, 2 over 2. Now, 2 over 2 simplifies to a 1. And look, we already have 1 on the list. So we're not going to write it again. This is actually just giving us a duplicate. So we'll just keep moving forward. We already have that one. Okay, let's move to a Q value of 3. 1 over 3. And then we'll go here, 2 over 3. Okay, and then the last Q value is 6. So we get this combination, 1 over 6. And then this combination here, 2 over 6. Now let's see here, 2 over 6 can simplify to 1 over 3, which look, we already have on the list. So this gives us another duplicate. So we're not going to write that down. Okay, and we've gone through all the possible combinations here. So this here is the list of possible solutions to this equation. Okay, if this equation has any solutions that are whole numbers or fractions, it's guaranteed to be on the list. That's what the rational root theorem tells us. Okay, so we're going to stop there. This is what it asked us to do. Find all the possible solutions, and that's what we did. It doesn't say solve. If it said solve, then what we would do is you could start with any one of these you wanted to. Maybe you start with positive 1, plug it in, right? Parentheses for each x, plug in a 1. See, does it equal 0? If it does, that means you found your solution. So you got one of them. Here, this is a degree 3. So that would be one of your 3 solutions. Then you do synthetic division, get your quadratic factor to find your other 2 solutions. Okay, but yeah, you might have to try a number of these. Maybe it's negative 1/3. I mean, maybe that's the solution. And you won't really know until you try them by evaluating on a calculator. Okay, let's go ahead and look at the second one. Let's try this one here. So let's do the same thing. Here's our equation. If we have this equal to 0 and we want to figure out possible solutions, P over Q values, let's start with our P numbers. P numbers are going to be factors of the constant term. So factors of 40. Now here, our constant term technically is negative 40. Doesn't really matter if you consider it positive or negative, because when we write down our P over Q's, we're going to do plus and minus on all of them anyway. So we're going to consider all the possible and negative choices. Okay, so factors of 40, what do we have? We got 1 times 40, 2 times 20, 4 times 10, or 5 times 8. All right, that's quite a few. So we got 1, 2, 4, 5, 8, 10, 20, 40. And then our Q values are going to be factors of 2. And that's only 1 or 2. Okay, so our possible solutions here, every combination of P over Q. So that's every combination of fraction we can get here. So let's go ahead and write these down. Now, starting with the Q value of 1, as I divide these numbers by 1, I just get the same number back, right? 1 divided by 1 is a 1. 2 divided by 1 is a 2. 4 divided by 1 is a 4. So that's going to give me all whole numbers of those same numbers. So let's do this. We'll list them out here. And you know what I'm going to do so that I don't have to write plus or minus for every single one is I'm going to wait till I get the whole list, and then I'm just going to put brackets around it and put the plus or minus outside. So I'll show you here. So we're not forgetting about the plus or minus. We'll come back and do that. Okay, so that's dividing every P value by 1. Now let's go to 2, right? Divide by 2. So we've got 1 over 2. Okay, now here when we go 2 over 2, 2 divided by 2 is a 1. That's already on the list, so we can skip that. 4 divided by 2 is a 2. That's already on the list, so we can skip that. 5 divided by 2, we don't have that one. Okay, let's see. 8 divided by 2 is a 4. We already have 4, so that's a duplicate. 10 divided by 2 is a 5. We already have 5 on the list. That's another duplicate. I think the rest of these give us duplicates. 20 divided by 2 is a 10. That's already there. And 40 divided by 2 is a 20. That's already there. Okay, so this is all of them. Here's our list. Now I'm going to do this. I'm just going to put curly brackets around them. Put plus or minus out here. Okay, so these are all the possible solutions for this equation. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers, but possible solutions are either the positive or the negative of all 10 of those. So that's actually 20 different possible solutions. Of course, all 20 are not possible, are not true solutions. There's only three solutions there. Okay, but any solution that is either a whole number or a fraction, it's guaranteed to be on this list. That's what the rational root theorem tells us. These are the possible solutions. Again, it doesn't ask us to solve, so we're going to stop here. But if you were to solve, then you'd have to go and check, find one that is a solution, and then do synthetic division. Okay, for this next section, it says find at least one rational root for each polynomial. So we're going to find one solution that works. So that means we'll generate the list of possible solutions, then plug them in and see if we find a solution. And look, what does it tell us here in bold? When we plug the x value in, if it equals 0, then that x is a solution. That's what we're looking for. If we get a 0, we found a solution. If it's not a 0, then it's not a solution. Okay, so take a look at this equation here. And hopefully this looks kind of familiar. This is actually the exact same equation which we were working with right here. And so we've already found all of the possible solutions, right? This equation here for number 4, same one. These were our p-values. The only q value was a 1. So when we did p divided by q, we just got those same p-values back. And these here are the possible solutions. So these numbers could be positive, could be negative. All right, so let's see. Let me just bring that list over here if I can. All right, there we go. All right, so look, those are possible solutions to this equation. And let's actually make this an equation here, right? Equals 0. We want to figure out which of these numbers, when we plug it in for x, do we actually get a 0. So this is what it's going to look like. Let's copy down the equation, replace every x with a set of parentheses. Plus 24 equals 0. So we're going to plug in a number. Now you can pick anyone to start. I guess I'll just start with, I'll pick positive 1. Okay, positive 1. Let's do that. Plug that in, positive 1. And this is what I want to know. Is it actually equal to 0? Now, let's see here. When I plug that in, I'm going to use my calculator. Actually, I'm using Desmos. I don't think you're going to be able to see it, but you can plug this in on Desmos calculator or just on your handheld calculator. Let's see, what do we get? When I plug in a positive 1, okay, I'm getting a 9. I'm not getting a 0. So you know what? That means positive 1 is no good, okay? Maybe I don't want to cross that off the list until I check negative 1. Let's do this. All right, positive 1 didn't work. Let's try negative 1. So now plug this in on your calculator. When I plug in a negative 1, I get 23. So again, not a 0. So 1 doesn't work. Neither positive 1 nor negative 1. Okay, so we could just keep going down the list. You don't necessarily have to go in any particular order here. Um, you could go straight to 24. It doesn't really matter. I'll go in order. So let's see. I'll try positive 2. So when I plug in positive 2, I get a negative 16. So positive 2 also, right? If you plug in a positive 2 here, that doesn't work. That's no good. Let's try negative 2. And when I plug in a negative 2, Oh, it looks like we found a winner. When I plug in -2, the function evaluates to a 0. So you should see 0 on your calculator. If you're doing it in Desmos, type it in on Desmos, you get a 0. And that's how we know that we found a solution. So actually, -2 does indeed work. So this is what we've got here. X equals -2 is a solution. Let's see. Find at least one rational root for each polynomial. Okay, we've done that. We found one rational solution. Now, of course, we know that since this is a degree 3 equation, there's going to be a total of 3 solutions. This is only one of them. To get the other two, you could keep checking on the list, and maybe the other two are on there. It's also possible that the other two solutions are not on the list because they could be irrational numbers. They could even actually possibly be imaginary numbers, which we haven't seen those as solutions to a degree 3 equation yet. But if you remember when we did our quadratic equations, imaginary numbers or complex numbers are a possible solution. So it's also possible we have complex solutions here. So what you want to do here to be sure that you can find the two remaining solutions is you do synthetic division using a -2 and using these coefficients. Okay, here, I'll just set it up for you. I'm not going to solve it because this problem doesn't ask to solve and find all solutions. I'm kind of doing some extra here, but just so you see, this -2 goes here. Don't change the sign because this is a solution. Use our coefficients from here. So that's going to be a 1, -8, -8, 24. Okay, and then you could do this, and the quadratic down here, you could solve that to get the last two remaining solutions. But we're done with this. We did more on this one than we actually were asked to do. So we're done with this one. Okay, next one here, same thing. We're going to find at least one rational root for this polynomial equation. We'll make it an equation equal to 0. And I just noticed that this equation is also one that we were working with before. We actually up here already solved and found the possible solutions, right? Number 1 up here, exact same equation. So these are all, let me see here, let's copy these. All of these right here are the possible solutions. So let me bring that down here. Okay, that's what we got. Those are the possible solutions. So we're going to do the same thing here. We're going to plug these in. We're going to evaluate the equation. So I'm going to write my equation, 6x cubed, but I'm going to replace the x with parentheses. 29x squared minus 19x plus 2. And we want to find a value that makes it equal to 0. So pick a number. Any number doesn't really matter where you start with. Maybe we'll start with, hey, look, we could start with this, -1/3. Let's start there. So we'll plug in -1/3 for each of these. And then this is a question mark here. We want to know, is it equal to 0? If it is, we found a solution. Let's go ahead and check. Now, of course, to evaluate this, you got to use a calculator or use a Desmos calculator. You're not going to be doing this by hand. So you're not going to be able to see my screen here, but I'm going to go over to Desmos and type this in. Okay, and negative 1/3 doesn't work. When we plug it in, we don't get a 0. So we could cross that one off the list. So maybe I'll do this. Okay, the negative didn't work. Let's see. Let's try positive 1/3. Try that. Evaluate that on your calculator or on Desmos. Again, that one doesn't work. Okay, it's not equal to 0. So that's, we can cross that off the list. We try both of those. So it's neither, maybe I don't want to circle that. I'll just do that. Okay, it's neither positive 1/3 or negative 1/3. Okay, so what's it going to be? Well, I'll let you try some of these, right? Plug some of these in, see if you can find the value that when you substitute it in for x, it satisfies the equation and makes it equal to 0. Okay, and then once you've taken a look, hopefully you can find it on your own. Or if not, either way, once you've given it a try, come back and check and we can compare answers here. Okay, I found it. Did you find it? This is the number that I found, and I think this is the only one on the list that works. Negative 2/3. When I plug in negative 2/3 for x, it does indeed equal 0, which means we found a solution. So here we'll have x equals negative 2/3. That's a solution. We haven't found all the solutions, right? Again, this is a degree 3. This equation is going to have 3 solutions. But this problem just asks us to find, it says find at least one, and we found one, so we could stop there. If you wanted to find the other two, you do synthetic division. You do it with these coefficients, and you do it with negative 2/3 as your k value on the top left. And yes, you can do synthetic division with the fraction. Might get a little bit ugly, but you know what? It should actually work out. It should give you a remainder 0 in the synthetic division, and then of course whatever quadratic is left over, you solve to find the last two solutions. Okay, that's that one. Okay, so here we've got a flow chart for solving polynomials using the rational root theorem. And you know what? The only part of this that's new right here to this set of notes, the rational root theorem, is the very first step, right? Step 1, use the rational root theorem to find possible zeros. So we make the list of all the P over Q possibilities. Those are our possible solutions. And then this is what we do. We're going to check each one, and using a calculator is the most efficient way to do it. Plug it into the equation, see if you get it equal to 0. Once you get it equal to 0, that means you found a solution. And that's actually what we were already doing, right? We were starting off with a couple choices. We plug it in to find the one that equals 0. And then we use synthetic division. That's the second step. Once we find a solution, we're going to use synthetic division. And you see what it says here? To reduce the polynomial's degree. So for example, if we start with the degree 3, do synthetic division, we end up with the degree 2, which is a quadratic. Once it's a quadratic, then this is what we're going to do. Factor the quadratic. And that's going to be with bottoms up, right? You could do A times C on the top, B on the bottom. You look for the two numbers that multiply to make the top, add to make the bottom. Once you find them, divide by A. That's how we can factor the quadratic. Or you know what? If it's not factorable, meaning you try this and you're like, I can't find any numbers that'll make this work, then guess what? You use the quadratic formula. Quadratic formula is guaranteed to work. Okay, so Once it's a quadratic, you're going to solve the quadratic either by factoring or quadratic equation. Now, if after you do synthetic division, it's not a quadratic. So let's say, for example, back over here, you start with the degree 4, you find a solution, you do synthetic division. Every time you do synthetic division, the degree drops by 1. So if it starts as x to the power 4, after synthetic division, it's x to the power 3. It's a cubic. It's not a quadratic. So after you do synthetic division, if it's not a quadratic, then this is what you do. You go back to step 1 and 2. So what you're going to do here is, and you can use the list that you already have of possible zeros, but you find another one. You're going to have to find another one. Okay, and then once you find that second solution, you're going to use that second solution and do synthetic division again, not with the original degree 4 polynomial, but with the degree 3 that you have after the first round of synthetic division. And then after you do synthetic division the second time, then you'll have a quadratic. So you're basically going to have to do synthetic division as many times as it takes to get down to a quadratic, and then you solve the quadratic here. Okay. And then your final step, collect all zeros. All right. Or in other words, all your solutions, put them all together. X equals, right? If it's a degree 4, your final answer is going to look like that. X equals 4 different numbers. And that's your final answer. It is possible that you get the same number twice. You could have a double solution. So that's possible. But you do need to have a total of 4. All right. That's the flow chart.